Okay, so let us begin, because we continue this series of our seminars. And today we have a speaker, Dorothee Haroske. She is a bright representative of the Jena school. So, Dorothee, you are welcome.
Thank you very much for this kind introduction, and also for this wonderful opportunity to be here in Cambridge with this wonderful weather, and everything is nice. So I'm looking for some. Almost everything is nice. There's no chalk.
No, there's chalk on the blackboard.
Yeah, there is. Yeah, on the blackboard down here. Yeah, okay. Fine. No, yeah, okay. Color. Yeah. No, I found something right. Yeah, it's fine. Perfect. Thank you. Yeah, but I found something here. It's fine.
I think it's basket.
But I think there's something. Okay, it's fine.
See,
Yeah,
they
yeah.
want that not only you are bright, but the top is bright.
Okay, thank you very much. So, maybe just a few words to the beginning. As you've heard, I'm coming from Jena, and this is the Triebel School of Function Spaces in some sense as well. So what I'm usually doing is I study function spaces, and now you see here this word sequence spaces. I mean, there are also spaces at least, but not the type of spaces that we usually study. And maybe just something to begin with a function space, and then to explain a little bit the motivation why at this time I'm going to talk about sequence spaces. So the starting point maybe could be some Morrey function spaces, some function spaces of Morrey type, and maybe just to start, everything I'm going to speak about today is either related to the Euclidean D space or to the lattice set D. So I missed this here, so this is the space defined on RD. Okay, what are we doing? We take some locally p-integrable functions, f, and we take the integral over the ball centered at x, this radius r, as any positive number, and then we balance this expression here. We multiply it with some r to the power d, this is the volume of the ball, multiplied with 1 over u minus 1 over p, and as you have seen here, or you may see here, 1 over u minus 1 over p is essentially negative, or non-positive. So what happens? If you have this integral, the last one term here, of course this is growing, if r is growing, but then you have some shrinking factor here in advance. It's the same if r tends to 0. So you look for the worst case, or some balanced explanation, construction here. And this is what is usually called at least one type of Morrey space. There are different approaches, and this is the one that I'm going to use for the function spaces, or to remind you. This is Mr. Morrey, and when he introduced this concept, he didn't call it Morrey spaces, but he used something that if you have something for the function in its gradient, it has some type of regularity like that, then you get a little bit better smoothness. This is what he used. Later, in the 60s of the last century, Campanato and Prudny, and you see a lot of famous names here who contributed to this. But then there was some time where not so much happened with these spaces, I would say. And the Renaissance quite recently, maybe recently, 20 years ago, has to do with some application, but I will come to this point very much later. So these are the Morrey function spaces, and maybe one of the most, my favorite example for such a function belonging to the Morrey space would be something like that. If you think of something like x to the minus d over u, and here's some cutoff function, so this is say C0 infinity, doesn't really matter, and something which cuts off everything else near 0. Then one can easily prove that this belongs to this Morrey space. There's not a big problem. It does not belong to the U space, obviously. Of course, this one, as I have a compact support, would belong to any space LR if R is less than U. That you do not need to be the Morrey space. But now if you take this as a starting point and you construct something based on this, say, as a very simple construction, you shift, you take infinitely many copies of this, and you shift it. Maybe let me call this nk. Yeah, you take these bound functions, you shift it all over the space, where mk are the shifts, are something like 2 to the k. So you have all these peaks at certain distances. And this function still belongs to the Morrey space if P is strictly less than U. But of course, it does not belong to any other LR space. So this, in some sense, explains a little bit or gives you some idea about this local global behavior. These are the Morrey function spaces. Obviously, if P would be allowed to be bigger than U, then this
function is not locally integrability.
In some LP? You mean that one? It doesn't. Yeah, it is.
Your example.
Yeah, it belongs to the Morrey space here.
But it's not log from LP log. No?
It is an LP log. If P is less than U, I mean, then you have only locally some finitely many. I mean, you have there are disjoint points where there are. I mean, if you whatever ball you take, you have only finitely many inside. I mean, this is drawing here. So 2 to the k, you have. So if P would be admitted larger than U, then it's not very interesting. And if P equals U, then you just get the LU space. So these are the function spaces, but as I said, these are not so much interest now, but studying function spaces of this type, one quite often needs some decomposition. In particular, what we use, or what we use in some other respects, and I come to this much later, are decomposition techniques like atomic decomposition, wavelet decompositions. And this means that, I don't want to switch it off. So once you have a function, say in a function space, and you ask whether, say, if this belongs to some first function space, it belongs also to some second function space. So you ask for embeddings, for instance. What one usually does is nowadays that to try to find some corresponding sequence space, say by some wavelet or atomic decomposition, and then ask the similar question for the sequence spaces. And if you are lucky, then you are come back. And therefore, so these are the sequence spaces, and these are the function spaces. And for that reason, it's very much of interest to know also something for sequence spaces. And this is, I mean, these decomposition methods, I will return to this point at the end. They are well known, and some of the most easiest examples would be the Morrey sequence spaces. I mean, these are just, as you will see, then there are something like the basic example, smoothness 0. So the idea is once you can understand the Morrey sequence spaces a bit better, then maybe you can understand also the more elaborate one that will turn out if you come to the smoothness spaces of Morrey type later. Okay, and there's a second reason why we study this, and this is one of, at least what has happened to me, the few rare cases that somebody at a conference asked whether there are some Morrey sequence spaces. I mean, this was in a conference almost 2 years ago, Banach-based operator theory in Poznan. And then we checked the literature and we found that there are essentially almost no papers on this. And almost no means there was just one paper submitted by Gunavan, Kikianti, and Schwanker, and they studied something like that. But it's the only paper that is concerned with these Morrey sequence spaces in the sense that we are studying them. There is another paper by Bereshnoi, but it's not really that Morrey sequence spaces. He used decomposition methods and then studied these. So in some sense, at least as far as known to us, this is the only paper about these Morrey sequence spaces, which was a bit surprising as it is not so strange to study this subject. And the paper that we are produced afterwards together with my colleague Leszek Skrzypczak from Poznan is now more or less online appeared in constructive approximation. It's just accepted some time before. Okay, and this is the topic what I'm going to present you the results is essentially from that last paper. So what are our Morrey sequence spaces? The Morrey sequence spaces are built essentially like the Morrey function spaces. So what we have a cube, and sorry for this strange notation from the theory of wavelets or atoms. Usually one has this kind of notation that you have QJM as the dyadic cube with side lengths 2 to the minus j sitting at say 2 to the minus jm, and then you add something like that. What we need here is usually the bigger cube, so we have this a bit probably strange notation. This has side length 2 to the j, and this would be the point 2 to the jm. So in our case, j is positive here, as you can see here, positive, so 2 to the minus j are bigger cubes. Okay, but apart from this, what we are doing? We take again p less than u, and then we take all sequences of complex numbers such that the following is true. We sum up all the coefficients lambda k, where here we have the unit cube sitting inside, where this lattice point is inside this q minus j. So the corresponding unit cube is inside this big cube. And then we take all these corresponding indices. We sum it up to the power p, and then we multiply it by the volume of this bigger cube q minus jm raised to this negative power again. So it resembles in some sense really the more function space construction. And as I said, all is the d or rd. One can extend this definition also to u equals infinity. I mean, you would just have this one, but it is more or less easy to verify that in that case, as it is for function spaces, in that case, it's just nothing else than L infinity. So it doesn't really make sense. I mean, you can do it, but you don't get anything new. So for us, essentially, p is less than u is less than infinity. And maybe just to keep it for later reference. So what we have here is Morrey function spaces. So we take the supremum over all big cubes this time and all lattice points, such that you multiply the volume of the big cube to the power, and then you sum up over all these cubes, unit cubes that are in the big cube. Okay. So some examples first before we come to some properties. Here's the definition in called again. Obviously, the constant function is not in. I mean, as you can see, if we are now, of course, interested in the case if p is not equal to u. So if this is 1, then you get here the volume of the cube to the power 1 over p, but then you have here the supremum over all bigger and bigger cubes to some positive power. This is, of course, not finite. So it is not identical with L infinity in some sense. But even if it goes to 0, it doesn't really help if it goes not fast enough to 0. So if you have something like a sequence k to the minus epsilon, then one can more or less easily calculate it. If the epsilon is too small, then still this sequence does not belong to the Morrey sequence space. So it is a null sequence, but it doesn't belong to the Morrey space. And this is an example. It needs a bit more care. This was in the paper that I mentioned, the only, or maybe first one paper that we found, this by Gunnar, Dicyanti, and Schwab. They considered this sequence k to the minus d over u, just as limiting case, and this again belongs, it resembles in some sense, if you look here, my favorite example from the function space. So this is just also for the sequence spaces. It belongs to the sequence space, but not to LU. And again, maybe something like this construction here. If you have a function that has ones at certain points, infinitely many ones, but not so many, then this belongs to MUP, the sequence again, but is not an LQ, of course, for any Q as it doesn't go to 0. Okay, so these are a few examples just to tell you what happens. Now some properties. It is a quasi-Banach space, where quasi means that you have the quasi-triangle inequality if p is less or u is less than 1. And otherwise it's a Banach space. Obviously, if p equals u, now you can have a look here. If p equals u is just LP or LU, whatever you want. And by means of Hölder's inequality, they are ordered in the second index. So they get larger and larger if the p gets smaller and smaller. There are always, for all p and u, subsets of an infinity, so you have bounded sequences. And for those who know, if you take the Lorentz sequence spaces, then you have to involve the non-increasing rearrangement of a sequence. And they are a bit larger than the usual LU spaces, so you have some monotonicity in the second index. I don't want to give you all the details. So the Lorentz sequence spaces, also well known, but still the biggest Lorentz sequence space LU infinity is still embedded into the Morrey space, and it's a different kind of extension if P is less than U. So it's really an extension in that sense. And if P is less than U, so you have not the LU case, then it's non-referable. And we have this kind of this homogeneity, which might be sometimes is quite helpful, of course, but this is not so difficult. So there are just a number of, I think, interesting results, and in some sense also they have some counterparts for the function spaces, at least if you are familiar with the function spaces results. Some of these results were also obtained before, but not on the sequence space. Okay, these are the spaces. Now maybe some other view on this. If you have sequence spaces, then you have, of course, the well-known scale LU, the little LP or little LU spaces. But there are also existing other sequence spaces which at least appeared implicitly in my examples. So let us look at the convergent sequences, these null sequences or the finite sequences, by which I mean that you have only finitely many entries that are non-zero. If you equip all these with the sup norm, the L-infinity norm, then it is well known that this is a closed subspace C0 of the, say, convergent sequences. And if you take the closure of these finite sequences with respect to the sup norm, then you just get the C0, the null sequences. This is well known, it's just a matter of some function analysis, probably. Okay, what happens now with the Morrey sequence spaces? All these sequence spaces, of course, are subspaces of L-infinity as well as our Morrey sequence space. So we have to look whether there is whether we can compare them in some sense. And for this, we introduce some notation. So we say that M0, these are just the Morrey sequences that are also null sequences. And if you recall our examples, we had some null sequences that were not in the Morrey sequence space, for instance, this k to the minus epsilon. And we had some sequences that were in the Morrey sequence space, but not in the null sequences. This was that one with the 1 at certain. So, I mean, this is not just MUP or C0, this is really a smaller part.
Sorry, what is null sequences?
So now, going to 0.
Null sequence.
And this is one notation, and the other one would be just to take the finite sequences, but take the closure not in the L-infinity norm, but in the MUP norm. And then to see what happens. I mean, as I said, if this is the L-infinity norm, then the closure of this space here would be just the corresponding C0. But now we have, of course, a different norm. And what comes out is the following, which might be interesting also for later comparison. So all these, as I said, all these are subspaces of L-infinity. Okay, but the Morrey sequence space is incomparable with the sequences going to 0 or to some other limit. As if you remember, as I just recalled a little bit, if you remember the examples, then there are function sequences that go to 0 but are not in the Morrey space and conversely. So in that sense, they are not comparable. And what about this construction here? Both the Morrey sequences that are going to 0, as well as the closure of these finite sequences in the Morrey norm, are proper closed subspaces, but in fact, this is different from the different from the situation if you have the L-infinity norm. There, the closure of the finite sequences led you to the null sequences, but here it's different. It's properly embedded into that. So really, if you think about these sequences, they are something new and they are incomparable apart from the trivial case, of course, when you have the P equals U, but essentially we are interested in the situation when P is less than U. There are really some other subspaces of L-infinity that might be helpful. And maybe some short remark to the function spaces as well. I mean, we have chosen, the first authors have chosen to call these the Morrey sequence spaces, but why? I mean, there is some connection with the Morrey function spaces. that are not written here, but probably remember. I mean, this was just the supremo of the balls and the centers. Then you had here the volume of the ball, and here instead you have this integral. If you have a sequence that belongs to this such a Morrey sequence space, then trivially a function where you take the characteristic function of the unit cubes belongs to the corresponding function space. This is not difficult to prove. So if you have a lambda, so maybe let's call this lambda, then the corresponding function built just by this is the characteristic function of unit cube sitting at k for some caller is just in the MUP. But conversely, if you have a function that belongs to the Morrey function space, then you can construct a sequence lambda 0 which belongs to the Morrey sequence space in the following way, that you just do something like you integrate your function f0 v1 over p. I think that's just should be working. Yep, with a p, exactly. And so in that sense, there is some correspondence between sequences and functions from the Morrey sequence space to the function space and vice versa. This is linear, this is highly nonlinear. So I mean, this is not an isomorphism or something like that. So it's really only to argue why it is reasonable to call these Morrey sequence spaces as the Morrey function space already existed. So I think this is a good reason. So what are we going to do with these Morrey function spaces? Some embeddings first. We found the following characterization of the embeddings, of continuous embeddings between two different Morrey sequence spaces, namely that they are embedded if and only if u1 is less than u2. This is not so surprising, as if you think this is something like LU, little LU, this is something like little LU2 with some extension, so one would expect at least something like that, u1 less than u2. But these defined indices here are also involved, namely this is continuous if and only if we have this condition coming from the outer LU space in some sense, and P2 over U2 less than P1 over U1. And obviously nothing, this embedding is never compact, as otherwise you would immediately have a contradiction that little LU1 into L infinity is compact, which is not true. Okay, but we have a characterization that this is true if and only if this is not surprising, but this is the new addition from the Morrey fine parameters, so to say. Just to compare it with some function spaces results, there is a result of Piccinini in his, not a PhD thesis, but some related article, but he worked on this in his PhD thesis, that if you consider the function spaces but now restricted to the cube, then there is a result that this is embedded if and only if. And now we have here the separate conditions, P2 is less than P1 and U2 less than U1. Of course, U2 less than U1, it has to do with the different ordering of the LU spaces. And this result was extended by Rosenthal in 2009 to the RD setting. Then, of course, you need U1 equals U2, otherwise you cannot compare it. But this is the trivial one. What this also says is the only one. They are monotonically ordered, but there's never another embedding if you do not add any smoothness here. But we have no smoothness at the moment. So in some sense it is a combination of both. And there is a very astonishing point, but I come to this later, to this condition here. Okay, but some consequences. This is the result, I just reported. What does it mean? It means, of course, that they only coincide if all the parameters coincide. But maybe it's more interesting. If you say that U1 equals P1, then we have the LU1 space here. And if U1 equals P1, then you have this condition. But if U1 equals P1, this is 1. But as you see, this is always required for the spaces, that they are not trivial. So it means that LU1, the usual little LU space, is contained in such a bigger Morrey space, if and only if it was already contained in the smaller LU2. You do not gain anything while extending this space. Even worse, if you restrict your target space to be U2 equals P2, to be a little LU space, then what you find here, if U2 equals P2, this is 1, but this quotient is always assumed to be less than or equal to 1, so the only possibility is 1. So it means you have only an embedding of such a Morrey space into a little LU space if it already was a little LU space. So no, well, this means, what is a bit surprising, if P is strictly less than U, so we are really in the Morrey situation, then you have an embedding in, you have never any embedding into LR, this is what is written here, as long as R is less than infinity. But of course, you always have embedding into L infinity. So there's really a jump. It really leaves the scale of little LR spaces. There's never any embedding. There's a counterpart for smoothness spaces of Morrey type in the function space side, which also has this, at least in some sense, for us, surprising result. So they really live in a completely different area. Okay, this is the situation with the continuous embeddings. Now, duality in Morrey spaces, Morrey function spaces, is a rather difficult matter. There are a lot of papers. Some construct some pre-duals, and this is what we also tried now for the Morrey sequence space. We tried to construct some pre-dual, and I think I can erase that one. Is it okay if I leave it here, as otherwise it always switches off? Maybe sometimes I don't like it too much. Let's make copy of it.
So can you have multiple pre-duals for that?
Probably yes, but we have only one. This is not usually. So what is our idea? What we construct, and then I will give you the idea. Maybe first, okay. Here are some results for the function spaces. There are some partial results. The earliest one, I think, is Sorko in 86, and then there are, as you can see, some later results on this. Also in the book by, no, I think in the book by Adams, probably is also mentioned, but there's a paper with Adams and Zhao in 2004 and some other. Probably there are a lot more other things, but yeah, these are at least are the ones that we know. Okay, this is a difficult matter. What are we doing now? So we look for some space that where's the dual, whose dual is the Morrey space. And our construction is, roughly speaking, the following. We construct some partial spaces XUP and take then the sum of them. And just to give you an idea, this is, roughly speaking, something like the intersection. This should be. Okay. So, the intersection of these. Okay, then we have these spaces here are something like, then you have some, say some constants, some weights here, but this is essentially something like L1, our spaces here. So what we do is, this is something like L1, which is, again, something like, this is now some tilde, L infinity, more or less. And this is just our Morrey space, that you take the supremum over all J at some level, then we have here the supremum over, as you will see then, the cubes, and this is just the appropriate, this is something like 2 to the J, D, 1 over U minus 1 over U, just the constants that we needed. So this is essentially the construction that we will do, and now I will give you the first definition of these members, X, these level spaces, Xj. Here it is, Xj UP, so we have a fixed level, and then later we sum up. Xj UP is just the following, we have here this factor from the weight that we need later on, and otherwise we just sum up the cubes inside the bigger cube, now with the power of P prime, as you think what we want to have in the end, P prime and 1 over P prime, and we sum it up over all points n. Okay, this is the level space Xj UP, And what we can prove then that this is, for fixed j, it is just equivalent norms in 2L1, but the norms depend on 2 to the j d over u. So I mean, this is really, this equivalence of norms is here for fixed j, is meant for fixed j. However, if we embed it into LU prime, then we indeed have norm 1. But otherwise, I mean, I don't claim, and it's also not true, that this equivalence is independent of j. This is of course not true. But for a fixed j, here, we have that essentially this space is just L1. As one can but this is not too difficult to calculate. Okay, these are the level spaces as that I mentioned here, x, j, u, p. And they are essentially L1 with some factors. And now, as promised, we take the sum of these level spaces here, x, u, p, and equip it with the usual sum, usual norm of such a space, taking the infimum over all admissible decompositions of the lambda. And then it turns out that this is the space that we wanted, and here are some results. It is located between L1 and LU prime, with both norms r being 1. It's a separable Berner space, as in fact the canonical norm is just an unconditional basis, the En, so where you have only a 1, 1. Okay. So this is the canonical norm. So En, canonical basis. And this is just and then this is the unconditional basis in this case. So it is separate. And the result that we wanted to have is that this space XUP, what comes out here, is just a predual of MUP. And that, on the other hand, the dual of this, and what was M00UP, this was just a closure of the finite sequences in this Morrey norm. This is isometrically isomorphic to XUP. So this is the result. And what we did, we looked a little bit for the construction, but for Morrey function spaces, as presented in this paper by Rosenthal and Triebel. So we, in some sense, we got some inspiration from there to construct our arguments. Okay, this is the result that we constructed a predual space to Morrey sequence space. Pitt's compactness theorem. Once we had the predual, we could use some other construction and construct some result which resembles the classical one by Pitt. And the result reads as follows. If you have a q less than p, and a bounded linear operator from LP to LQ, where the q is less than p. I mean, this is not the interesting point. Or from the null sequences into LQ, then every such bounded linear operator is automatically compact. And this is due to Pitt in 1932. There exist different proofs apart from those presented by Pitt. Here are some names, at least, that we found who studied this question later, also for sequence spaces. So Defan, Lopez, Molina, and as you can see, here are some papers, but not so many, at least we found. Okay, this is an interesting result. We found at least that whenever you have a bounded operator in such a situation, then it is automatically compact. And now we have a counterpart for that point. Now C0, I mean, is close, but not is identical to our space with the Morrey spaces. Our counterpart is a counterpart to this part. If you have an operator which is bounded from the Morrey sequence space into LQ, then it is compact. So we have P less than U, and both are bigger than 1. And any bounded linear operator from T, from these were the closure of the finite sequences in the Morrey norm, any bounded linear operator is even compact. And here we benefited from our result was a pre-dual as we adapted a short proof. I mean, this is a really nice paper. A short proof, it's really short, as you can see. Short proof of Pitt's compactness theorem using some of the things that we had already before. So we found this paper and we seen that there the pre-dual argument was involved, and though we can use it as well and transferred it to our situation. There is only at least one question. I mean, this is a nice result, and it would be even nicer if you would have some examples for for bounded linear operators acting from M00 to LQ. I mean, just to have some results. There is at least one preprint now on the way from the more or less a subset of the first three authors that I mentioned, Gunawan, Hikyanti, and Schwab, and they studied at least some operators in the Morrey spaces. So maybe we can find some operator which maps boundedly from this Morrey space or this closed subspace of a Morrey space to LQ, that to apply our results. Unfortunately, I have to admit we have no operator so far. I mean, it's a nice result, I guess, but no application so far. If somebody has some really nice operator acting in these spaces, I would be very grateful for knowing this. So, I mean, it's just a theoretical result at the moment. Compact embeddings. Unfortunately, there are never any compact embeddings in these Morrey sequence spaces, as I mentioned, as there are no in the little LP spaces. But in fact, one of our motivations, and I come to this at the end, was to study compact embeddings in function spaces, and then we need some auxiliary results in there. Maybe first, we consider now finite dimensional Morrey sequence spaces. Of course, this is some escape. If you have a finite dimensional sequence space, then they are always compactly embedded. This is, of course, not a very big surprise. So we consider for the moment a cube of fixed side length. So this cube is now always, the outer cube is fixed, say for some level j. And then, of course, we only look for those smaller cubes inside here, the smaller cubes here, and we just count their numbers 2 to the JD, and this index set for all these for all the k where the related unit cubes are inside the bigger one is kj. It's just an abbreviation for the definition. So and now the finite sequence spaces are the following. So they have something like dimension 2 to the JD, and now we only take those indices, no, not the indices, those entries of the sequence where the corresponding unit cube belongs to the bigger one, but at most to the very big minus 2 to the minus j0. This is the outer cube, everything happens there. Okay, these are the finite sequence spaces. I think it's the standard way. And then one can calculate the norm of this embedding. It's not very difficult. And essentially here, as you can see, I mean, if there are just the usual LU spaces, 2 to the JD, then you have either norm 1, this is just the monotonicity, or otherwise by Hölder you have 2 to the JD, 1 over U2 minus 1 over U1. So, and here we get something similar, where in only one case you can see that if P1 is bigger than P2, then you really have some influence of the fine parameters, otherwise not. As then really it matters whether this is P1 equals U1 or P2 equals U2, this would be the case here. But if P1 is bigger than P2, as you can see here, then you really have some additional influence. And now we come to compactness. In compactness, you can measure in different ways, of course. One way to measure compactness is via entropy numbers. What's the idea? If you have a compact operator, then it maps a bounded set, say the unit ball, to a pre-compact set. And then you have only finitely many epsilon balls which cover this image of the unit ball. And now the idea of entropy numbers is just to fix the number and ask how small you can get all these balls uniformly to make it smaller and smaller, but the number is fixed, that still they cover the unit, the image of the unit ball, which is written here. So you ask for the smallest radius of such balls, such that you can still cover the image of the unit ball in the first space, in the second space, and the image of the unit ball from the first space in the second space by these m entropy numbers. And for some reason, this more is of some advantage to look for the dyadic entropy numbers. This is well known. It's a well-known concept. It has a lot of nice model graphs. So you can look for the details. It's a long history. For us, the main point to study this is also applications. I mean, not here in this talk, but what is usually quite interesting is applications in spectral theory. That there's this famous Triebel inequality. Which tells you that if you have a compact operator and you order its eigenvalues by decreasing modulus and count it according to their multiplicity, then it comes out that the entropy number of these, that the eigenvalue was number t of this operator can be estimated from above by the entropy number of this operator. And I mean, there's a more refined version of this, but this is the way it usually is used. So if you are in a Hilbert space situation, then you also can use, maybe even with some better results, approximation numbers or other numbers, like here, further similar concepts, S numbers. But in the Banach space situation, quite often the entropy numbers give a sharper upper estimate. This is the main reason for us to study this, but not here, but this is the main reason to study entropy numbers. Okay, and then it comes usually to the famous Schütt result, who studied this in '84 for the finite dimensional little LU spaces. This is the result. He calculated also the dependence on the dimension, as you can see here. This is well known. He did it for the Banach space situation, and then it was extended later. And our result reads very much similar. I mean, this is just, we have 2 to the JD, this is our dimension here, the 1 over U2 minus 1 over U1, these are the main integrability parameters. And then you have this 2 to the minus K, 2 to the minus JD in the exponent here. This is true in this setting only if the K is sufficiently large, which is in some sense also the most interesting case. There are some partial results for smaller K, but maybe it's not so interesting here. And the main point is that we use, of course, we use our norm estimates that we had before, and then we travel around these two commutative diagrams and apply the submultiplicativity of the entropy numbers, and then essentially we can get what we want. So this is the main point. So entropy numbers are well known. Finally, as I promised, I come back to the function spaces and to some reason why we studied this. As I said, we are in the end more interested in function spaces and compact embeddings. And now here comes some function spaces. Function spaces, for instance, first of years of time. So this is the Fourier analytical approach, probably very short, but okay. F is the distribution from S prime. You apply the Fourier transform to F, multiply it with some compactly supported smooth function. So the phi j are a smooth dyadic partition of unity, meaning that at any point where you sum up, you end up with 1. They are supported in essentially in annulus with radius 2 to the j, with some overlap. And there are C infinity functions. Okay, smooth. And if you multiply this and take the inverse Fourier transform, you get some smooth function. So you measure this in LP. You multiply it with the 2 to the JS, which is the corresponding weight factor for this annulus. and measure all this in little LQ. This is, I mean, last week we had the definition of Besov spaces via differences or moduli of continuity, and now this is the Fourier analytical definition, but they coincide. They're equivalent in the norms. Okay, this is the Fourier analytical definition of these Besov spaces, and it's well known that the Schwarz spaces are contained in the subspaces of S prime. What I call the classical ones would be those with the differences or moduli of continuity defined. Well known, if PQ equals infinity, then you have the Hilbert-Zsigmund spaces. If it's P and Q equal 2, then you're on a Hilbert space setting and they coincide with the Sobolev spaces. And if you interchange the norms here, the little LQ and the big LP norm, then you get the Triebel-Lizorkin spaces, and they coincide, of course, with the Sobolev spaces. This is well known. So these are the Besov spaces. And now if you look at this definition here, and therefore I've chosen the Fourier analytical approach, then what the people did was the following, just to ask what happens if instead of LP as a function space, LP on RD, if instead of LP we extend it slightly by the Morrey space. So we make it a little bit larger. And this is what happened. So they replaced, otherwise it's literally the same. So they replaced LP by this Morrey space. Nothing else happened. And this is the approach that was chosen by Kosono and Yamazaki in their paper. And they really have applications. I mean, they used it to study the semilinear heat equation or Navier-Stokes equation with the distributions in new function spaces initial data. And the new function spaces are just those. Why they have chosen the N, I don't know. There are different stories. I don't find any convincing, but nevertheless, N stands for the Besov-Morrey space. So they have chosen it, and all other people later have taken this over. And then there's another paper by Mazzucato who studied also these new function spaces and obtained some results. If P equals U, then of course you end up with the Besov spaces again. There is a parallel approach, and also here I don't know who invented the number E, but the letter E, but if you just interchange it, then you get Triebel-Lizorkin-Morrey spaces. There are quasi-Banach spaces. So a lot is known meanwhile about these spaces, about these Besov-Morrey spaces, NSUP. And just to end where I began, I said that there is some reason, which is the reason is now disappeared. The reason was that quite often it is helpful if you have a function space that you use some decomposition to some appropriate sequence spaces. Then you argue there and you quite often technically easier sequence spaces and try to return. The appropriate sequence space here for this big N, the Besov-Morrey space, would be something like that one. So you sum up in some the coefficients in some cubes, multiply it, take a supremum, and then you have the little LQ norm also. And if you do so, then one can prove that using Dobschi wavelets, but compactly with sufficiently high regularity, there is a wavelet decomposition of these spaces, so that for the leading terms they belong to LU, and the other 2 to the d minus 1 terms that you need for your wavelet decomposition belong to this corresponding space n sigma UP, where you have the shift S plus D half if they are L2 normalized. This is not essential. So this is the main point, that we come from the function spaces here using some wavelet decomposition, Dobschi wavelets, compactly supported wavelets, sufficiently high regularity, that we can transfer it isomorphically to this construction of sequence spaces. And therefore, it is quite interesting to study these sequence spaces. And if you now forget about anything else, okay, little LQ outside, there is some weight factor, forget about it. But what you have here inside is in principle something like finite Morrey sequence spaces. You have here, you sum up some cubes into some bigger one, and you multiply it with some weight factor. The nu, of course, you can take out, the j you could take out, otherwise you have the nu here. So what really remains here inside, in principle, apart from the weight factors, is just our finite dimensional Morrey spaces. And this was, in some sense, one reason for us that we thought if first we can study the compactness of such finite dimensional parts inside, maybe this helps us for the compactness of the spaces here on domains. And the surprising thing was that this is well known. I mean, for these corresponding sequence spaces, we have also a complete result that they are embedded if and only if, and then you have here this something like the Sobolev case that you have this same differential dimension in both spaces. And if you now look for that, this was proved in 2012 already. If you look for the limiting case, so you have just something like a Sobolev embedding. S1 minus d over u1 equals S2 minus d over u2, and maybe even with the same q. Then we have that this embedding here, belonging to the Morrey function spaces, no, these are the Morrey, the smoothness Morrey sequence spaces if you want, is embedded if and only if we have this condition, and this you have seen before. This is just the same condition that we obtained for our Morrey spaces. Unfortunately, we do not know why. I mean, both theorems are correct. And so, I mean, this is if and only if, as this is just the same here. We haven't not yet found a really convincing reason why this should be the case, that if you pay enough smoothness here and here, so you eat all your smoothness that you can from the Sobolev embedding, but why this is just equivalent to the basic spaces to be embedded, it is so, but I don't know why. I mean, this is just something interesting. But nevertheless, there are some ideas to study this also for other numbers. In fact, what is here open question is not really, I mean, the third point is half open, I think. As we obtained quite recently and submitted some entropy number results for the function spaces, and there have also some surprising outcome. I can sketch it quickly, but otherwise this is only a first result here, but there is a lot more is open. Of course, it would be nice to have some, there are a lot more sequence spaces, more function spaces, also to study the sequence spaces, and as I mentioned, to find applications for operators. I mean, there is something like, people do something like discrete harmonic analysis, but we haven't, I mean, to say I only know that there is something, but we haven't found the connection yet, and maybe we find some operators where it is helpful to have these Morrey sequence spaces. What we found for the Morrey function spaces, this is really the end. Is the following, these are the spaces, the function spaces. And if you think of RD, then we have necessary and sufficient conditions for the continuity, but of course they are never, as it is in other spaces, in Besov spaces as well, they are never compactly embedded. But of course one can think about their restriction to smooth domains, C infinity domains, no problem at all. So then we have compactness here, that this gets compact if S1 minus, I mean this is well known already. If this is sufficiently large, one can write it down, and all the p's are included, then we have a compact embedding. You have to have enough smoothness here. Difference of smoothness should be sufficiently large. And then one can ask for the entropy numbers if you have a compact embedding. And the surprising fact is that usually, at least for those who have seen entropy numbers before, what usually happens in such cases is that they don't care for the p's at all. The usual behavior would be just the difference of smoothness divided by the dimension. This is the rate, how fast the entropy numbers go to 0. This is the usual case. And this is recovered in most cases here. But the interesting part is that if apart from one case, which I'm not going to write here. And this is if the smoothness parameters are sufficiently close. You still have compactness, but they are just compact, so to say. Then by sudden it appears that really the new parameters, not the Q ones, these are the fine parameters, but the P, the Morrey parameters, that they really enter the scene and you really get a different behavior of the entropy numbers here, which at least was not so to expect. I mean, we assumed that with sufficient effort we can prove that whenever there is a compact embedding we have this. As this was the situation in all known related embeddings. I mean, not if you speak of different smoothness, of course. If you have a generalized smoothness, then it's different. But if you have the smoothness S1 and S2, always it appeared like that. And so it was a bit surprising that, in fact, in this Morrey situation, in the function spaces, we have something new. But this is not the topic of this talk, and therefore, I thank you very much.
Questions, comments,
Or answers. Operators.
answers here?
So in the case of Morrey function spaces, there is a wavelet characterization in terms of subsequence.
Not wavelet. I mean, if you, okay, you can use it if you use the
Not the Besov-Morrey,
Yeah, yeah.
just the
Yeah, I mean, if you use the identification with the E0, I mean, if you can just go this way, then you have something. Not directly, but if you use that NUP equals E0 UP2, which was proved by Mazzucato as P and U are bigger than
is the
is the
Triebel-Lizorkin type.
Triebel-Lizorkin.
Okay, with one
Sorry, but this
no,
is
okay,
yeah.
yeah.
And they have a wavelet characterization, and in that sense, you have it here.
And the sequence space is not the same you use.
Well, the problem here is, I mean, we tried, but here we have just sequences of index bank K, and then, I mean, this is not so easy to find the counterpart here, as there are different smaller cubes. I mean, we had some idea like that, but it's not so clear.
Yeah, exactly.
Yeah, would be nice, but yeah, so far at least we have not found any connection. So this is Mazzucato theory.
Other questions? If it is not the case, let's take the speaker. So we are done for the day.